Hey guys. So in this video, we're gonna we've pretty much done, except for the first problem, most of homework 16, just in the videos for note 16. And the ones that we haven't done are down here, predicting solubility using KSP. So if you haven't already, hopefully you had 15 or so, maybe 20 minutes to work on these two problems to the best of your ability. If you haven't, pause, work on them, have a little struggle moment, and then watch this video and I'll show you how to do it. So switching cameras. Again, homework 16, molarity and concentration. And we are doing problem number 8 and 9, which both use this table. That table, I literally just copied and pasted from the table that you have in your notes. I just didn't use the whole table. I just picked the two that you needed from here for the problems and pasted them there so that you didn't necessarily have to look up lead to chloride and find the number. Now notice it is a little bit different. This one says 1.2 times 10 to the 5th for lead chloride. And this one, same exact formula, says 1.7 times 10 to the negative 5th. It just depends on which textbook you use. Each textbook kind of has slightly different reported answers, but it's all going to give you a similar answer. Like this one is 1.6 times 10 to the negative 10 for the KSP of silver chloride. When I find silver chloride in the notes, it's 1.8 times 10 to the negative 10 instead of 1.6. But what I say as a good rule is the problem will always tell you the information that you need. This table here was just to give you an idea of the range and scope of all the different K values. But anytime you're doing a problem on your homework or on the AP test, if you need the KSP, they will give it to you. Don't memorize KSPs. Okay, so back to that. Number 8, using the table above, will a precipitate form when 150 milliliters of 0.1 molar lead nitrate combines with 100 milliliters of 0.2 molar sodium chloride? We are under the assumption that both of these are soluble. 150 milliliters, 0.10 molarity lead nitrate. 100 milliliters, 0.2 molar sodium chloride. Even if you didn't know that those were soluble, we know they are because they're getting mixed together. But this has nitrate in it. Nitrates are always soluble. And sodium chloride, sodium is in the 1+ column. 1+ salts are always soluble. So we've got soluble over here, soluble over here. So in reality, this isn't necessarily stuck together. There's Na+, Cl- floating around. And over here we have nitrate, 2 of them. 2 nitrates, and the lead must be 2 positive charge to counteract that. So all of these are floating around. Choices on how they could combine. We could put the nitrate with the chlorine, but that's not going to be a precipitate because nitrates are always soluble. Actually, I just misspoke. The nitrate with the Na. We don't want to combine negative and negative charge. That just wouldn't work in general anyway. Let me get a marker and fix my mistake here. So these were the original pairings, and now we're looking at new pairings. We could potentially put the NO3 minus with the Na plus, that's what I meant to say, but that's not going to be a precipitate because +1 and nitrate? No way, those are totally soluble. Alternatively, what if we put the Pb, the lead, with the chlorine? And that's our ticket. That's what we're looking at here. Lead chloride 2. That's the only thing that could potentially be a solid. I should fix this in the notes for next year. This is the wrong type of arrow. You don't ever want to do this type of arrow for equilibrium. It must have auto-corrected. We want to use the one that has an arrow one way and an arrow the other. So lead chloride, solid, dissolves into lead and 2 chloride ions. The KSP is 1.2 times 10 to the -5th. So I'm going to write this out as an expression. The K expression is products over reactants. I've got the lead, the chlorine, that 2 in the front makes it squared. I could put this here because it's a reactant, products over reactants, but I'm just going to end up taking it out because it's a solid. So my expression is K equals Pb2 plus molarity times chlorine molarity squared, and this is equal to 1.2 times 10 to the -5. I need to plug in values here and here. I need to plug those in and see if it exceeds this threshold. So let's try it. Where is the lead coming from? The lead is coming from here. I had 150 milliliters. The concentration was 0.10 moles per liter. Every time I have 1 mole of the lead nitrate, I get 1 mole of the lead. This is how many moles of the Pb2 plus. To get it into concentration, I have to realize that now this is getting mixed in with the concentration here. So what I'm going to do, I don't have enough space to do this on my paper, and I actually recommend that you do 8 and 9 on the back side of your paper so that you have enough space. But let me show you, I made an answer key that I can walk you through the answers. Screen share. So this says number 10, but it's actually number 8 that we're doing. So don't worry about that. But it's the same problem, right? 150 milliliters of the PbNO3. I drew it out. That's in 1 beaker. And we had 100 milliliters of the 0.20 molar NaCl. I drew that out. I showed how they mixed. To determine if it will precipitate, to determine if it will precipitate, we need to calculate K for our solution and compare it to the KSP threshold. We're not worried about the sodium. We're not worried about the nitrate. What we're thinking might precipitate is the lead and the chlorine. So this is as far as I had gotten in my paper before I ran out of space. K equals products over reactants. Wrote it down. Cl was squared. Take out solids and liquids. So it's just Pb2 plus concentration, Cl minus concentration squared. 150 milliliters, aka 0.150 liters, times the concentration, and the fact that every time one of these breaks apart, we get 1 of the lead. I got to that 0.015. That's where I had just gotten to on my calculator, this many moles. But now it's divided by 250 milliliters. That 250 milliliters is coming from the fact that we mixed 100 of this and 150 of this other to make 250 total. I converted 250 milliliters into liters. Okay, solve that through. Move my face. I'll move it over here. And that 0.06 molarity for the Pb2 plus, that's what I plug in here. I did the same process to figure out what's the molarity of the chlorine ion. There was 100 milliliters. The concentration was 0.2 molar. For every 1 sodium chloride, I get 1 chlorine. I have 0.02 moles of chlorine divided by 0.250 liters. They're both out of 0.250 because they both are mixed together. I get 0.08 molar. So I took those, moved it up into that expression, and I rewrote it down below. K equals 0.06 molarity times 0.08 molarity. Don't forget the squared. And let me double check that I did this right on my answer key, because sometimes I don't. 0.06 times 0.08. It's not even typing. Hold on. 0.06 times 0.08 squared equals 3.84 times 10 to the negative 4, which is what I have there. So I'm saying, is this value on my calculator, is this value more than the threshold in the table? Because if it is, then we get a precipitate. So let me switch my camera again. This is what I'm getting for my final answer. The threshold is 1.2 times 10 to the negative 5th. Is 3.84 times 10 to the 4th greater than 1.2 times 10 to the negative 5th? Yes, it is. We will have a precipitate PbCl2 will precipitate. That's your final answer. Will a precipitate form when these are mixed together? Yes. PbCl2 will precipitate because R value exceeds the threshold. The threshold being 1.2 times 10 to the negative 5. So let me go back one more time to the answers because that's what I wrote. I wrote 3.84 times 10 to the negative 4. This is greater than the KSP value given in the table. So yes, the PbCl2 will precipitate. In the notes, we did this problem here with the barium hydroxide and the iron sulfate. If you're interested, I wrote out the steps similarly on my iPad, but we already did this one in the notes, but I forgot to show you how this was if you want to scroll through this. Okay, so the last one, if you think you need an extra minute to fix your answers, go ahead and pause the video. But the last one here, I'm going to write out on a fresh sheet of paper, just so it looks nicer. So let me do that. A 500 milliliter solution of calcium chloride. Okay. 500 milliliters is the same as 0.500 liters of calcium chloride. And inside of here, the chlorine ion concentration is 8.0 times 10 to the negative 6 molarity. And this is added to (300 milliliters) converted, 300 milliliters of 0.0040 molarity of silver nitrate. Okay. So I'm looking at how calcium chloride, how would this split apart? Calcium, chlorine is a 1 minus ion and there's 2 of them. This is how that would split up. Silver nitrate. I could hypothetically put the calcium and the nitrate together, maybe. I could potentially put the silver and the chlorine together. Since this is a nitrate, this will always be soluble. So there's no way that this is our precipitate. This one is potentially our precipitate if we exceed the threshold. Maybe. I actually don't know if it will or not. I don't remember the answer to this problem. Potentially will precipitate. It looks like it will precipitate if we exceed the threshold of 1.6 times 10 to the negative 10. What did I say? 1.6 times 10 to the negative 10. All right, that's the number to meet or beat here. This is the KSP for AgCl, which divides into Ag plus Cl minus. My expression would be products over reactants, removing the solid. So just AgCl. That's my expression that I'm using. I need to figure out from this information given to me, this is how I will use, I'll get the chlorine info from that beaker. I'll get the silver information from this beaker, put them together and see if I beat that. I'm going to start with the silver. I need to get the concentration of the silver ion. I have 30 milliliters, concentration of 0.004. And every time that one of the silver nitrates breaks apart, I get one silver ion. This is how many moles of silver I have. Can't plug it in quite yet because brackets mean molarity. So I need to take this many moles of silver, moles per liter. How much liters are there when I combine these two together in a third beaker? At 500 milliliters, 300 milliliters. So I need to take this and divide by 800 milliliters, which is also the same thing as 0.8 liters. So I'm getting 0.0015 m. This is my concentration of silver. That is going to go up here. Same process for the chlorine. Except for this one's kind of already nice. It's already telling me the concentration of the chlorine over here. Why can't I just plug that in? That'd be so nice. Look, Cl minus, Cl minus. Does that work? Not really. Because this is the concentration of the calcium when it was in a tiny container. But we combined both of these into a bigger container, even though I'm drawing it smaller. that has 800 milliliters. So that's not the concentration anymore. We gotta figure out what is it now that it's diluted. So going back in the notes here just a little bit, it's still in note 16, but it's the formula for, where is it? Dilutions. It's on page 1. We're just taking this, and when it gets added from 500 to 800 milliliters, it's diluting. So M1V1 equals M2V2. This is the dilution equation from the very beginning that we used earlier in the homework. So, where's my marker? M1V1 equals M2V2. If the concentration before, the concentration of the chlorine before was 8 times 10 to the negative 6 molarity, when the volume was 500 milliliters, what is the concentration when the volume has now changed to 800 milliliters? Milliliters. I run it through. 8 times 10 to the negative 6 times 500 divided by 800 equals, so the concentration this is the molarity of the Cl minus ions in the combined beaker. Notice, yeah, it's less, duh. It's went from 8 to 5 because the water went up. It's more dilute. So this is going up here. We have to decide with these numbers getting plugged into this expression, do we exceed the threshold? Will this precipitate? So let's plug it in. Ag times Cl. That was the expression that we got. Ag 0.0015, Cl 5 times 10 to the negative 6. There was no squared or anything. Moment of truth. Is this bigger than this? At first glance, my brain got it backwards because I was like, no, 10 is bigger than 9. But think, scientific notation. 10 times 10 to the negative 10 power. This is smaller than our value. We have exceeded it. 7.5 times 10 to the negative 9 is greater than 1.6 times 10 to the negative 10. I should have scooted that down. Sorry. 7.5 times 10 to the negative 9 is greater than 1.6 times 10 to the negative 10. That was the threshold. If we exceed the threshold, then yes, 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 there will be a precipitate. AgCl will precipitate because our value was greater than the threshold.